In today's session, we'll discuss about resonance in electrical circuits, and through this session we'll be able to define the phenomena of resonance in RLC circuits, both series and parallel. We'll try to find out the condition of series resonance and the corresponding resonance frequency of the circuit. We'll plot the graph of various circuit parameters at resonance, as well as finally the resonance curve. We'll calculate the resonance frequency of a practical resonator. So what is resonance? Resonance is a frequency matching phenomena in which frequency of two or more objects or circuits is matched using the filtration process. Filtration is normally done either by accepting or by rejecting the desired frequency. The commonly used filters in our daily life are shown in the figure, and we'll try to understand the phenomena of resonance with the help of a simple analogy based upon these filters. The process of accepting and rejecting of these frequencies can be tried out using a simple filtration process. These are very simple, commonly used filters in our daily life, and we're going to use these filters in two different ways. First one is the process of accepting a particular material with the help of these filters. This filter will work as acceptor, but under the condition it will allow the desired material to pass through its holes if material size matches with the size of its hole. The desired material in this case is this liquid T. However, the process of rejecting is a bit different. Suppose we are having a mixture of pulses, and we'll have to filter out these pulses with the help of the same filter. But in this case, the operation is a bit different, that this same filter will not allow the desired material to pass through its holes. That is, if the material size is bigger than the size of its hole. So in these two different cases, in first case, the desired material is passed through the filter. However, in second case, the desired material is rejected by this same filter. In the same way, we are having two different electrical circuits known as series resonator or acceptor, and a parallel resonator known as rejector. These two filters use the property of a coil and capacitor. A coil, that is inductor, stored energy in magnetic form, and a capacitor stored energy in electrostatic form. In first kind of filter, the circuit components R, L and C are connected in series, and in second case, the coil and capacitor are connected in parallel. Sometimes parallel circuits are also known as tank circuits. So we'll now discuss about resonance in these electrical circuits. Resonance of a circuit involves capacitors and inductor. The magnetic field of inductor generates an electric current in its winding that charge the capacitor, and then the charging of capacitor provide an electric current that builds the magnetic field in the inductor, and the process repeat itself. But what happens at resonance? At resonance, particularly in series circuit, that is the case of acceptor circuit, the impedance Z is at minimum value. Why it is minimum? Because the effect of inductive reactance is being cancelled out by the effect of capacitive reactance, and net resistance or net impedance of the circuit is only resistive. In case of parallel resonator, the impedance is maximum, because in this case the admittance or the reactive part of the admittance becomes 0, and again the net resistance or net impedance of the circuit is only resistive. But in case of parallel, normally we are going to use the reciprocal of R, that is 1 by R. So for minimum resistance, it is clear Z is 1 by R or 1 by Z, or Y is 1 by R. In this case, the impedance will be maximum. Resonance is used for tuning and filtering because it occurs at a particular frequency for a given values of inductance and capacitance. Now, particular case of a series resonator, when resistor, inductor and capacitor are connected in series. Definition wise, when an RLC circuit is connected along a fixed voltage but variable frequency supply, then at a certain value of supply frequency, a condition reached where magnitude of inductive reactance, that is XL, which is directly proportional to frequency, is equal to the magnitude of capacitive reactance XC, which is inversely proportional to frequency. As they both are complementary of each other, hence they will cancel out the effect of each other, and under this condition the total impedance of the circuit is minimum and is pure resistive, that is Z equal to R, because XL minus XC becomes 0. The circuit current is maximum, as current is the ratio of voltage with respect to impedance, but here impedance is only resistive and normally will take very low value of resistance. So under this condition, the circuit current is maximum. Maximum circuit current will cause maximum voltage drop individually across the reactive parameters, that is inductor and capacitor. And this voltage drop across either inductor or capacitor is normally very, very high as compared to the supply voltage. And due to this property, these circuits are also known as voltage magnifier circuits. Remember, series resonator are acceptor as well as voltage magnifiers. Now, as the circuit response or the impedance of the circuit is only resistive, that's why the circuit power factor is unity. Because in case of pure resistor, both voltage and current share the same phase angle. The phase difference between the applied voltage and the circulating current is 0 degree and cos of 0 is unity. The frequency at which this phenomena occurred is known as resonance frequency, normally denoted by F0. Now we'll try to find out the mathematics behind this resonance frequency. Expression of resonance frequency: at resonance we know that XL at resonance, that is XL naught, minus XC at resonance, that is XC naught, is equal to 0, or XL equal to XC, where XL can be defined under resonance condition as omega naught L and XC as 1 upon omega naught C, where omega naught is 2 pi F naught. It gives omega naught L equal to 1 upon omega naught C. Finally, omega naught equal to 1 by square root LC. So here we can find out resonance frequency F0, which is only and only depending upon the value of inductor and the value of capacitor, that is 1 upon 2 pi square root of LC. So here, by knowing the value of inductance and knowing the value of capacitance that is connected in our circuit, we can easily find out the point of resonance or resonance frequency. The graph plotted between various circuit parameters. Graph A representing the graph of inductive reactance XL. These graphs are plotted with respect to frequency. All the circuit parameters like XL, XC, Z or R on vertical axis, while the supply frequency on horizontal. In graph A, we are going to plot inductive reactance XL, as XL is directly proportional to frequency. At frequency equal to 0, the curve will start from origin at certain higher value frequencies, as XL is directly proportional to F, this is a linear curve, or it is simply a straight line which passes through origin. In case of XC, as XC is a reciprocal of frequency, the graph B shows rectangular hyperbola. The algebraic sum of XL and XC is the graph C, which cuts the frequency line or cut the horizontal axis at the point of resonance. Now, curve D represents impedance Z, which is equal to square root of R square plus XL minus XC square. At XL minus XC equal to 0, this graph will touch the line where impedance is equal to resistance. It is the point of resonance. Here the impedance is minimum and the corresponding current will be maximum, that we can find out with the help of resonance curve. A resonance curve is the curve plotted between the circuit current on vertical axis versus supply frequency on the horizontal axis, as current and impedance share a reciprocal relation. The graph of impedance was almost inverted parabola, but in case of current versus frequency, we can find out at F0, that is at the point of resonance, the circuit current is maximum, as shown in the graph. The value is Im. Prior and after this resonance point, the circuit current is normal RMS current, that is 0.707 times Im. These 2 points prior and after the resonance frequency are known as off resonant points, or sometimes known as half power points, because at these points the power is exactly half as compared to the power at resonance. Now, we can also increase the amount of maximum current by reducing the value of resistance. In that case, the curve will be highly selective. A highly selective curve means we can easily achieve the point of resonance. In that case, the total duration between F2 and F1 represents bandwidth. Bandwidth is a particular band of frequency, and about this resonance curve, the bandwidth will represent the off resonant points as well as the point of resonance. Now we'll try to find out various circuit parameters of a practical series resonator. In this question, there is a series resonator. All the value mentioned as resistance equal to 1 ohm, capacitance as 10 microfarad, inductance as 100 millihenry, and this combination is connected across a 1 volt supply source with variable frequency at the input. We'll have to find out first of all the resonance frequency. We'll have to calculate the current at resonance and the corresponding voltages across inductor and capacitor. And finally, we'll have to comment upon the results. Now, for the first case, we know that resonance frequency having the formula 1 upon 2 pi square root LC. So we can easily calculate the resonance frequency for this given circuit as 159.235 Hertz. We can find out Imax as V upon R, because at resonance, impedance is only equal to R. So it is 1 upon 1, which is equal to 1 ampere. Now the voltage across inductor will be this current at resonance multiplied by inductive reactance at resonance. It is equal to 100 volt. In the same way, the voltage across capacitor will be the product of resonance current multiplied by XC at resonance. So it is again equal to 100 volts. So the third point is, here voltage across inductor and capacitor is magnified by a factor of 100. The supply voltage was 1 volt only, but the individual voltage drop across inductor is 100 volt as well as capacitor as 100 volt. As both are complementary of each other, the total voltage drop together will be 0, but individual voltage drop is many times high. That is the main reason why these circuits are known as voltage magnifiers. So this will conclude our session, and the next section will discuss more about selectivity and parallel resonator. Thank you.